So I'm going to talk about this 2017 paper, Understanding Deep Learning Requires Rethinking Generalization. So for some background, just to make sure we're on the same page, we're defining generalization error to just be the difference between training error and test error. Deep learning models tend to have high generalizability compared to other approaches, and this is despite the fact that they tend to have way more parameters than many other machine learning models relative to the number of training samples. However, some models have better generalizability than others, and it's actually not well understood what dictates which deep learning model will have good generalizability versus bad generalizability, or at least it wasn't well known when this paper was published in 2017. So this paper is trying to explore that territory and learn more about those processes. So for their goals, they wanted to use permutation methods to explore generalizability in neural networks, explore the role of regularization, and challenge current hypotheses of generalizability. So as for data sets, they use these classic labeled large data sets, CFAR10 and ImageNet, and essentially they're just fitting different deep learning, using different deep learning approaches to perform image classification with primary focus on this inception framework, which is a deep CNN architecture developed by Google. They also consider AlexNet, a smaller version of Inception, and also just traditional MLPs. And I provided a little schematic of Inception here. So what was their approach? So in the traditional image classification situation, we have a bunch of labeled images, and we want to just train a neural net and compare training and test performance. So sort of as an example, here's what they did. And they did this using the Inception framework on the CFAR10 dataset, so 10 classes. They found a training accuracy of 100% and a test accuracy of 85-ish%. So that's a generalization error of about 15%. But then this is where they did something weird. They, instead of properly labeling each of the images, they just randomly labeled them. So they called this a fork, this a lion, and so on. And so they want to know, in this situation, what is the training and test accuracy? So you would guess the test accuracy can't be any better than random guessing, because there's no correspondence between the training labels and the test labels. But the surprising finding was actually the fact that the training accuracy was still 100%. Even in this case where there's no natural correspondence between the label and the image, the labels are completely random. The net was able to memorize the image and its associated label and achieve perfect training accuracy. So they also provide this graphic that shows sort of the rate of learning over time. So we have, for the true labels, there's zero training accuracy after 5,000 steps. In the case of random labels, we have a lag period where it takes longer to learn, because the underlying structure doesn't really make any sense. To like, two images are labeled as cat, one is a trash can and one is a tree or something. So it takes a while to sort of organize some structure, but then once it starts memorizing the images and their labels, the learning actually takes place quite quickly. And in 15,000 steps, there's zero training accuracy. So, and then they consider other kind of randomization schemes in between the two that I'm not going to go into here. So this defies expectations because, first of all, they're surprised that once fitting starts, it converges quickly. Also, the fact that they don't need to change the learning rate schedule to achieve high accuracy in the setting. And the primary surprising finding is that simply they fit the training data perfectly in this setting. So the implication, again, is that these models are memorizing the images and their labels instead of learning underlying structures that are generalizable in a different context. So it suggests a large role of sort of overfitting to the training data via memorization. Poses challenges for several traditional approaches for reasoning about generalization. I'll give one example of this Rademacher complexity measure, which is used sort of a mathematical construct that determines the complexity of hypothesis classes of a certain model and is used to construct sort of theoretical bounds on the generalization error. But because this paper showed that basically no matter what form the training data comes in, even if it's sort of randomly distributed pixels, random labels, 100% training error is possible. It sort of renders this measure sort of theoretically useless. And then I just want to talk quickly about regularization, which is also relevant to the idea of generalization in these models, and they studied a little bit. So here's a couple terms of regularization methods that we talked about in class, at least some of them. And then just showing sort of the results on these models. Let's just focus on inception. So we see random crop, that's a type of data augmentation, and weight decay. When these are both turned on, we have quite high test accuracy, 89%. When they're both turned off, test accuracy goes down a little bit. So that's suggesting that these regularization approaches are improving test accuracy. But it's surprising that no matter which are turned on versus off, there's still 100% training accuracy in each case, suggesting sort of a lower cost in the bias variance trade-off to regularization for models like the inception model that are deep convolutional neural nets. And then one more thing, this is just another graphic showing that when we turn on data augmentation, weight decay, and dropout, we have the highest testing error, but it comes at a small cost of training error. So I think we've been through these. I'll just go to the conclusion. So deep CNNs are often rich enough to memorize the training data, even with nonsense images and labeling. So we should be wary of that fact. It poses conceptual challenges to current understanding of generalizability, since most theories fail to incorporate this fact and rely on the implicit assumption that it is false. And there's more work to be done to understand generalizability in deep neural networks. Thanks.